Okay, welcome back everybody. We are now in the last section of Chapter 12 in our Calculus 3 class notes. We are on page 22. And this is just a handout that I extracted right from our textbook that helps you kind of see what the different shapes are that we're going to work with mostly as far as quadric surfaces. So these are ellipsoids, which are very much like a sphere, except that they're elliptical in every direction. Okay, so it doesn't necessarily, they have an equation very similar to a sphere, right? If a squared, b squared, and c squared were all the same value, this would be a sphere. Okay, then we have what's called an elliptical paraboloid, or I just call it a paraboloid. Z equals, if it was z equals x squared plus y squared, then you'd have just a nice parabola and the zy and the zx planes, and then as they trace out this bowl-looking figure. Okay. This is an elliptical cone where instead of z equals x squared plus y squared with maybe constants underneath, we have z squared equals x squared plus y squared. So this traces out cones both above and below the z-axis. And then you have hyperboloids. And hyperboloids, you have a hyperboloid of one sheet. They have this general equation. You have a hyperboloid of two sheets, which has this general equation, and a hyperbolic paraboloid, which looks like a saddle, right? And we will talk about these. These are very interesting points later where notice that this point right here is called a saddle point. It's a maximum if I were to look at it in this direction, but it's a minimum if I were to look at it in this direction. So it's an interesting point, and there's a lot of calculus behind that we're going to have to learn and explore to understand those types of points. But those are really the quadric surfaces that I need you to know. Most importantly, I would expect you to be able to draw an ellipsoid or a paraboloid pretty quickly. Cones, very similar, just you have z squared instead of z. The hyperboloids and of one sheet and two sheets and hyperbolic paraboloids, I don't really expect you to be able to draw, so don't worry too much, but I do want you to be able to recognize them. Okay, all right, so for example, I would expect you to be able to draw things like this. Let's say I asked you to sketch the surfaces 4x squared plus 4y squared plus z squared equals 16. If that had been a 4z squared, then we would have a sphere. But we don't, so we have what is called an ellipsoid. Then we have z equals 8 minus x squared minus y squared. So basically that's going to be a parabola. Instead of an upward spacing bowl, we have a downward spacing bowl. Just like if I had y equals minus x squared, right? Upside down parabola. Now we have z equals minus x squared minus y squared, which is upside down paraboloid. The 8 just means that when x and y are at 0, its vertex is up there at 0, 0, 8. Okay, I'm saying too much before I talk about each one. Okay, so starting off with how do I sketch an ellipsoid? First of all, I want to put it in a nice ellipsoid form so I can see where the intercepts on the axes are. So that means that I want to get 1 on the right-hand side of the equation. So I divide everything by 16. And then simplify that and make sure that the constants in the bottom are something squared. So this is x squared over 4, which is the same thing as x squared over 2 squared. This is y squared over 4, which is the same thing as y squared over 2 squared. This is z squared over 16, which is the same thing as z squared over 4 squared. Okay, which means that on the x-axis, I'm going to have intercepts of 2, 0, 0 and minus 2, 0, 0, right? X could be 2 and minus 2 for this to equal 1 when y and z are 0. Y can also be 2 and minus 2 for this to equal 1 when x and z are 0. And z would be 4 and minus 4 when x and y are 0. So those are its intercepts. And then you can see that. So then you just draw in the ellipses, trying to put dotted lines behind where it's really something you couldn't see from our viewpoint but would like to see the depth, right? So in the zx plane, we have this ellipse. It goes through the z-intercepts and the x-intercepts. In the yz plane, we have this ellipse, which goes through the y-intercepts and the z-intercepts. And in the xy plane, we have this ellipse, which actually this one's a circle, right? It has the same radius. So this is a circle. in the xy plane, which goes through the y-intercepts and the x-intercepts. And that's an ellipsoid. And then the paraboloid, again, just think, okay, first of all, you can see the vertex. When x and y are 0, z is 8. So there's the vertex. Because it's negative x squared minus y squared, that's an upside down. So then you can figure out, well, when y is 0, then x has to be plus or minus the square root of 8, or plus or minus 2 square root of 2. So those are the intercepts on the x-axis. And when x is 0, y would have to be plus or minus the square root of 8, also for z to be 0. So you can get those intercepts. And then you just draw the upside down parabolas in the xz plane and the yz plane. I probably should have drew this one dotted, sorry, because we couldn't see that one. And then in the xy plane, when z is 0, you're going to have x squared plus y squared equals 8, which is just this circle in the xy plane.